Good afternoon, students. Let's start our practice. Okay, is it okay with my sound?
Yes.
Good. Now let's start, and here now we will begin with you new session 1. We have finished with you session 0, and now we'll start session 1. Let me open my screen. So let's do it. Is it visible? Okay, now exercise session 1. Here we will study finite arithmetic in machine and loss of significant digits. So we'll start with the rounding of the numbers and the finding machine arithmetics. So you can see in the first example, consider a computer which uses floating point arithmetic with base n 10 and t is 5 digits for mantissa and rounding rule. Introduce the following numbers a and b. So first of all, are they machine numbers for us? First question. So to be machine numbers, it should be t is 5 digits mantissa, but in this case, how many digits in mantissa? 6 digits here. Yeah, so they are not machine numbers for us. And now, first of all, we need to do these numbers, machine numbers, and then find subtraction between a and b, so just a minus b, and then find machine subtraction after rounding. So if we round, it will be this mantissa, yeah? And when we round it, what will be here?
5 mantis.
So 4, 8, 3, and the 6 it will be, yeah? Because of here, the last digit is greater than 0.5. Is it clear?
Yes, yes.
And the second one is just 4, 8, 4, 1. So we have 5-digit mantissa. We will consider this machine number and round. And rounding rule, use rounding rule. So here 4, 8, 4, 1 it will be now. So let's write these numbers. So A is equals to, first of all, let's give format of number long E. It means after point, we have 4 digits here. So now let's A is equals to this number. So here point, and now semicolon, and B is this number. And semicolon again. And find A minus B. And denote by C, for example, it is. So you can see here, this is in format long E. So it will be after point, we have 16 digits, but we can use here just format short E. Short E. And let's do it one more time. And you can see here difference between them. So here we have just how many digits after point? 4 digits. So this is format short E. This one was format long E. Okay, now let's continue. And here find this rounding numbers. So it will be now, let's denote like a on the line. It's equals to 1, 4, 8, 3, and 5, and not 3 and 5 now, 3 and 6 after rounding, yeah. And then B1, new one, B on the line is now 1.4841 just. And now let's find new C underline. So it is equals to just A underline minus B underline with respect to this new machine numbers. And it's equals to this number now. And now find, so we have two kind of differences here. So the first subtraction, this is just exact subtraction, real subtraction. This one is machine subtraction. So we have two different answers here. In machine subtraction, this number. In real subtraction, this number we get. So they have difference between them. And if you want to find C minus C underline, so you get this difference. Is it clear? Now, however, we have difference, so we have error. And let's find this error that denoted by ER. And how to find error? Who can answer to this question? Error. Relative error. It was absolute value of C minus C underline over absolute value of to the real one with respect to this real subtraction. So now it's equals to this number. Is it clear?
Yes.
So we just find the relative error between them. When we round two numbers, we have errors. And error equal to this number. This is 10 to the power of minus 2. Okay, good. If it's clear, good. Now let's continue. Exercise number 2. So F1, F2, we have 4 following functions. And we need to define here. So X is given and N is also given. And now we need to reformulate our function. What does it mean reformulate? We need to change this given function with new function, which is algebraically equal to this function, but in machine arithmetics, they are not equal. And then when we change it, our function to new reformulated function, we have what? Relative error between them. And compare these two functions. And this reformulated function assume as exact value function. And with respect to this reformulated function, find relative error and graphically represent it. And here compare them with machine precision. What was the machine precision? This is machine accuracy, and it's equals to 2.2. Let me write here 2.22 times 10 to the power minus 16. So it's equals to this number. This is machine precision, accuracy of machine computing. Okay, now so here we have 16 digits of the point. Now let's write, first of all, given function. Let me clear all. Okay, now we will use format long E. And now n is equals to from 1 till 16 here, semicolon, and x is given also. So it is 10 to power of minus n. So it is 10 to power from 10 to power of minus 1 till 10 to power of minus 16. And now let's give the function f1 as f1, and it was 1 minus cosine x over x squared. So 1 minus cosine x. So here point division, because they are now vectors. We have 16 values of this vector. And for each corresponding value, we will find the value of f1. So x here also point power 2. And now we need to change this function to the new function. And what will be the new function, which is equal to this function? How can we change? Using trigonometric identities, we can change here. Do you have any idea here?
Sine squared.
Yeah, sine square half angle, x over 2 here. Yeah, this numerator. Let me write. So this numerator, 1 minus cosine x, it's equals to 2 times sine,
Right.
sine x over 2, half angle, squared. Like this. Is it clear?
Yes.
And now we can change this function to the new function. For example, f1, this one is equals to now, let's change it sine. So, for example, x over 2. And we can write like this, point division, x over 2.
Matlab screen is not.
Yeah, this is not Matlab screen, this is PDF file. We can copy. x2. So x2 and squared here. Like this.
Yes.
All of them in squared, of course. Here brackets and here also brackets. But here we have coefficient, so we need to multiply here just by 1 over 2. And now it's correct. Let's check it one more time. So it will be sine x over 2 over x over 2 squared. And in denominator, you'll get here x squared over 4. And this 4 goes to the numerator. And with this 1 over 2, it gives 2, this one. Is it clear now? So let's put our new function, reformulated function, to our command window. To our command window. So here, and let's semicolon again. And now find error, ER1, error 1, first function. Okay, it's equals to, again, absolute value of f1 minus error 1. Sorry, not error 1, f1, new f1. This one. And now here, point division. Why? Because of now they are vectors, not just one unique value we have. Here we have 16 values. So that's why here we have point division. And with respect to reformulated function, so it means a absolute value of new f1 underline. So let's continue. And now let's show the results in table. How we can do it in square brackets as matrix. So x, the first variable, the prime, and then f1 prime and error 1. Error 1. So let's show the result here. So we have how many columns? 3 columns. And you can see here the values of x from -1 till -16. And then in the middle, you have values of f1. So beginning the 1, 3, 4, it's 1. It takes just 0. So it depends on the machine position also. So it will be very small number. That's why here just 0 it gets. And then here you can see, however, they are zeros. Now it will be just ones without error any. But here we have errors. Is it clear?
Yes. But I don't understand this F1 underscore
underline
formula. 1 over 2 multiply.
1 over 2, because of here, you can see this is in numerator, this one is denominator, and all of them in square. So what was the exact function? Exact function was 1 minus cosine x over x squared. So here we just replaced 1 minus cosine x with 2 sine square x over 2. Yeah. So this one we get sine square x over 2. Just after that, we will compute the coefficient. And then here x square over 2. So here we don't have 2. And x square over 4 we will get here. However, 2 is squared also. And this 4 goes to the up and gives 4 here. But we need 2, not 4. That's why we just divided by 1 over 2. Multiply by 1 over 2.
And Professor, can you explain why we are using dots before division?
So, okay, dot division, this is division of vectors. So here we have 16 vectors. You can see from 1 till 16. So this is not one value, exact value. Here we have 16 different values of x. And for each x, we have own values for f1. That's why we will put here dot.
Okay.
Okay. If it is just coefficient, we don't put here dot. For example, here like this, x over 2. This is just 1 over 2. This is not vector. But when we're dividing vectors, we will put dot division, point division. When we multiply or when we do powers, etc.
Okay.
Okay. So what means in x f1 er1? So it means table as table. So you can see here in square brackets. So x, just we divided with this prime. The first column, this is x. The second column is f1, and third column is this absolute relative error.
Why you put this symbol
prime?
after x?
Prime?
Yes.
To divide them. Just dividing these columns.
Okay.
Doing table like this. So we can here add the fourth column also. For example, here after F1, we will add the new F1. This one, yeah? And space, of course. So you can see here, now the values of new f1 also here. Is it clear?
Yes.
And now we have the second part of our exercise represented graphically. We print the relative error for every value of x. You can see here, for every value of x, we have corresponding errors. Yeah. And now we need to represent it graphically. How to represent it graphically? Using commands plot or log, which we did in previous practices. So if you use plot in this case, this is not useful for us. It's not a good idea because of plot drew the graph in normal scale, yeah? But here we have what kind of x? They are tens powers. So if they are in tens powers, we will use here log logarithmic scale for both axes. So for example, let's show in plot also why it's not good. Plot, let's prove it. And here, the first variable x, then the error, because we need to represent it graphically. And then, for example, color, and then the line width. So, for example, 2. Okay, let's check it. So you can see here, this is not good graph because of this x's are very small. Is it clear why plot it's not useful for us in this case, in this situation? And now let's do it in log. The same work, but here let's change plot with log logarithmic scale in both axes. Log. So now let's check it, and you can see another graph here. Now our scale is from -1 10 to the power of -1 till 10 to the power of -16. And this is x-axis. This is axis for error. Is it clear?
Yes. For small numbers, we use log.
Yes, of course. For small numbers, we will use log. And we for tens powers. So here, tens powers we have as base.
Yes.
Okay, let's continue. So log just plot using logarithmic scale for both axes. Okay, now let's do the next function for f2 of x, e to the power of x minus 1 over x. Have to find here reformulated function, new function. Do you have an idea here? So however, we have e to the power of x. We can change this e to the power of x with expansion, Taylor expansion. with Taylor polynomial of e to power of x. We did the similar example in previous practice session, and we can change here e to power of x with Taylor polynomial. It's Taylor polynomial. Let's do it. So clear all. Now again format long e and give number n, then x we have here. And now let's write new function f2 it's equals to e to power of x minus 1 over x. Exp, yeah, we write e to power of x, exp of x minus 1 and the point division over x. Okay, now new function f2 underline. So how can we write here f2 underline? So let's do, what was the Taylor expansion for e to power of x? Let me write exp x is equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, yeah, and plus so on, and the plus, so the general term was x to power of I over I factorial x to power of I over I factorial plus etc. And the last one here is x to power of so let me, so here we have just continued here. Okay, and then we will find the last term also. So in this case, if we begin, for example, as the starting value of new function f2 as starting value, consider, for example, 1. So however, e is from 1 till so x over 1 factorial it will be if I is 1. Let's do in this form. So as here the starting value will be, for example, just 1 because of here first term is 1. Then continue for loop, yeah, for I equals to the cycle, yeah, 1 till 16, not without semicolon here, of course. And then write new function f2 equals to previous value plus f2, no, not f2 here, just now x, the main the general term, x to power of I dot power, of course, I over I factorial. So it will be factorial I, like this. And now, and. So we'll continue till 16. I from 1 till 16. And let's continue and find relative error. So we have already one relative error. So here now we have second one, error 2, and also f2 minus f2 new function, and absolute value of f2 new function. Okay, now let's do values, table of the values. So you can see here, sorry, this is for F1 and error 1, so the previous one. We need to change it. So let's change just ER2, F2, and F2 again. So now you can see here the result. So why this is correct? Because of, look here, if this e to power of x look here, and if I is 1, so it will be 1 plus x to the power of 1 over 1 factorial. This is just x. Is it clear? If I is 2, so it will be now, if I is 2, it will be exp x equals to 1 plus x, this is previous one now, yeah? We will add to the previous one, new term, plus, and now x second, x squared over 2 factorial. Is it clear?
Yes.
And so on. We can continue this process. So just what?
No.
If
the seconds.
Yeah, if I is 3, for example, yeah. So it will be exp x. Now we will put this I2, 1 plus x plus previous one over 2 factorial, and plus next one, third one, yeah, x cubed, yeah, x cubed over 3 factorial, etc. Do you understand me now?
Yes, understand.
This is cycle, and we can find all terms by this way for Taylor polynomial of e to the power of x. But we have here, we need to, this is not a new function. We need to subtract 1 and divide by x also here, yeah? This is Taylor polynomial for e to the power of x, but we will subtract. And divide by it. So that's why what we have here. So this is just finding e to the power of x by this way. And now This is not f2 new function. This is not f2 new function. It's just for e to power of x. Now let's do next step here. So this is just e to power of x. Now we need to subtract 1 and divide by x. Do you understand me? And when we subtract 1, we don't have here 1. This one.
Hmm?
This one. Yeah? It's just beginning with x. So new function now. Let me write here. New function. Now it will be f2, for example, new function. We denote with this one. Let's denote with e. Okay, this function now it's equals to, after division we have here 1, yeah, plus here now we have less 1 power, x first power, x second power, etc. X I minus first power. Is it clear? Because we divided by x. Now it will be 1 plus x over 2 factorial plus x squared over 3 factorial plus etc. plus x power I minus 1 and over I factorial. Is it clear now? We subtracted 1 and divided by x to our e to power of x. Do you understand me?
Yes. Got it.
Okay, so now we can work with other cycle also here. Let me write here, for example, let's clear all and then begin with new list. Okay, so let's and give x and give f1 f2, just f2 given function, and now we can do with this give here. However, now we have this function here, 1 plus x, this is last function, 1 plus x over 2 factorial, x squared over 3 factorial, etc. x power I minus 1 over I factorial, yeah? And now we can begin here, not from 1, from 0. Is it clear?
Yes, yes.
Because of if you write from 0, and now let's let's check it. And now here we have this 4 without 4 we cannot do it. So 4 I from 1 till 16, and let write this function, new function f2e. Where is f2e? So f2e, so with Taylor polynomial we have this. Okay, let's write f2e. So f2 underline e. So now it's equals to, look here, f2 underline e. So previous one plus, and now this general term we can write here, x, do you understand me? X to power of, now dot power of course, I minus 1 and over factorial I. So we have, this is not now expansion of e to power of x. This is expansion of new function, e to power of x minus 1 over x. factorial I. Do you understand me?
Yes, yes.
Okay, now divide by just
Yes.
and here now we have relative error now. ER. Now this is not F2, F2E. Just change it and just find it. And now find this table now. ER2, here E. So let's show the result here. So you can see here now another result, and let me clear all of them. So now we have two new function F2E. So we use here Taylor polynomial for e to power of x. But after putting e to power of x, 1 and 1 are canceled. And after dividing, we have this kind of formula now. I think it's clear now. Okay,
Yes.
now, yeah, let's do graph here with log. Where is our log? This one. So with log, so x, and now ER2 we have, yeah, just as second variable. And just check it. So this is now new graph of the relative error function. Is it clear, students?
Yes.
Please give your questions. Any questions? No questions?
No.
Okay, can continue now. So now let's consider the third function. F3 of x, it's equals to 1 minus square root of 1 minus x squared. How can we replace this function now with the new function?
Is this one? I wrote in chat.
Yeah, 1 minus x, 1, yeah, using this formula, yeah, doing rationalize this kind of irrational numbers, yeah. So here we have, let me write, so this one equals to, just multiply to conjugation form with plus and divide by it, yes. So 1 minus square root of sqrt 1 minus x squared, yeah, and it should be multiply. We need to multiply it and divide.
Yes.
And divide by this number, yeah.
But with plus.
With plus, of course, with plus. It's conjugation form with plus. Yeah. Now you can see here it's equals to, now they are canceled. So 1, if we open the brackets in numerator, 1 minus sqrt so you can see here this one and this one, when after multiplying, we get here 1 minus 1 plus x squared, so just x squared, yeah. Just x squared, and over this one, 1 plus sqrt 1 minus x squared, x dot power square. Let me put here also a dot. Everywhere we have dots. So, is it clear? How to get this function? And now let's copy this function. And let's write to the program. So let's clear all. And now, again, we have n, we have x, corresponding x, and then we have new function f3, yeah, f3 is equals to, so what was, just let me put it again. Here we have minus as exact function, yeah. This one was f3. Let me check one more time. 1 minus x squared. Yeah, and now new f3, yeah, f3 underline, and it's equals to this number, this function. Yes, new function. You can see here how we get it. And now let's find error. Error with respect to f3. Here f3 and here er3, for example. Find this error. And now as table show the result. F3 and F3. Is it clear? So we have here some kind of errors. So where we have error here. Here point, we lost point here, sorry. In F3. Should be point here. This is point division. Yes?
Yes.
And ER3, we lost our point here. And this one. Now it's correct. So you can see the result here. And now we can draw the graph using log. Let me put here ready one. ER3. Just show the graph. Yeah. Now this is our graph, new graph. Is it clear?
Yes.
So, and now here we can see the graph and the relative error. So in this table, you can see value of x, corresponding value of f3, corresponding value of new reformulated function f3, and f3 underline, and corresponding values of error, relative errors. Please give your questions now. So at home you can continue this fourth one and find the reformulated function.
It's the same as third one also.
Yeah, can be, yes. I think now it's not too difficult for you finding relative errors with respect to reformulated function. So again, we changed our function, and that's why we have errors between them, relative errors. They are algebraically equal, yeah, but in machine arithmetics, they are not equal. You can see here relative errors between them.
And these errors play important role in kind.
Yeah, if they are very small, it means this is good function to represent this function, to change this function.
We choose a function with the smallest error.
Yeah, so this is also called algorithm, yeah? We choose a correct way to solve this example. So we choose the correct function to solve it. For example, in this case, when it is cosine, we can, for example, use here tangent or cotangent also, any other trigonometric functions. Yeah, instead of sine. We can do it with trigonometric identity. We can get here other function also, but it can be not necessary for us. Okay. Any other questions, please?
Code.
Code. Okay. And one question: do you know how to get the history of comments? For example, like this.
Yes. Straight.
Yeah, with narrows here. And so, okay. If you know, good.
Can you show the code above?
Above? Here we just lost our dot. That's why here written horizontal dimension mismatch. You can see this is compute only for 1 by 1. Yeah. So here not vectors, but we have 16 vectors. But its division we take just without dot. It's not correct. Mismatch dimensions.
Yes.
So very important putting dot to compute as vectors.
Yes, clear.
Okay, any other questions, please? No questions?
No, I don't have.
Okay, if it is clear, we'll continue next time.
Okay, thank you.
Thank you for attention.
Goodbye.
Goodbye.